Hello everyone and welcome back. Today's topic is public key cryptography. So this area involves a lot of mathematics, especially in the areas of number theory, algebra, algebraic geometry, probability theory, and so on and so forth. So it is not something that we can discuss in a week. Especially we need all of these backgrounds to talk about public key cryptography. So it should be like 1 or 2 courses. So, and we don't have that much time. So we will try to see it like an engineer. So we will not go much further into detail in terms of mathematics. So we will try to see the little mathematics to understand what is going on and how we can use it. This area actually involves a lot of different topics. So in order to be able to talk about them, in the beginning, I will actually give you a lot of definitions from different areas. So let's start. So the idea of public key cryptography is first introduced by Diffie and Hellman in 1976. They wrote a fantastic paper titled New Directions in Cryptography, I guess. So in that paper, they describe how we can have a public key cryptography. So their idea is as follows. It is based on using a trapdoor function as f. So it takes some input p and produces some output c. But they name it trapdoor as follows. So in order to see it, let's first see the one-way function. So we can define a one-way function as follows. It is easy to compute the output. So given x, you can compute fx and obtain the output. But it is hard to invert f. So when you're given the output y, it should be hard to find x that gives this output. So you can think about hash functions at this point. So they are one-way functions. So Diffie and Hellman define a different way of function called trapdoor function. So the idea is almost the same. When given the input x, it is easy to compute fx. And it is hard to invert f without extra knowledge. But the people who has the extra knowledge, they can easily invert f. So it is easy to find the inverse of f with an extra knowledge called the trapdoor. So their idea actually is as follows. In symmetric key cryptography, we mentioned that the people or the devices they are communicating should have the secret key so that they can communicate, so they can encrypt and decrypt messages. So in this scenario, they say that if we can have a function f that is easy to compute, then everybody can use this f function to encrypt messages and send to the person they want to communicate. So everybody can send you a message, but only you who has the extra knowledge can decrypt them. So this is the idea behind public key cryptography. So actually, although they published this paper years ago, they received the ACM Turing Award in 2015 for their contribution of actually inventing public key cryptography and digital signatures and so on. So it is kind of a late award, let's say. And they also mentioned that they used some ideas from Merkle, so actually he should also receive the award, but only Diffie and Hellman received this award. So although they described such a function, in their original paper, they cannot come up with such a function. So later on, other people will give us this kind of functions like RSA algorithm or AlGamal and so on. We will see some examples. But in that paper, although they couldn't give us a public key encryption algorithm, Diffie and Hellman introduced a key exchange algorithm, which is still used, which is actually almost all the time used by us when we connect to a web page and so on. So this is actually one of the reasons they received the Turing Award. So let's see what the main task for public key cryptography is. One of them is confidential message transmission. So you can have public key algorithms to use for encryption and decryption. RSA and AlGamal are examples for this kind of algorithms, and we will see them in the following slides. But of course, they would not be as fast as symmetric key cryptography. So this is why most of the time we use AES instead of RSA and so on. Public key cryptography also solves the problem of authentication by using digital signatures. And we will see digital signature algorithm or standard also in the following slides. Public key cryptography also solves the problem of key exchange, which is exchanging the key of a symmetric key crypto system through an unsecure channel. So actually, this is what we are doing all the time. When we want to connect to our bank or to an e-commerce web page, we haven't communicated them before, so we haven't exchanged any AES keys to talk in an encrypted way. So in order to buy something from a web page, but we should use a secure channel, or we should use an encrypted communication so that we can give our credit card information and so on. So, but we cannot, e-commerce web page cannot go to everybody's house and give them a secret key for their communication. So this problem is solved by diffie-hellman with the diffie-hellman key exchange algorithm, which we are going to see in a minute. But first, as I told you before, I'm planning to give you a lot of definitions because they will be they will be useful for us to understand the following slides and following concepts. So let's start with complexity of algorithms. Let's define a polynomial time algorithm. An algorithm to perform a computation is said to be polynomial time algorithm if there exists an integer d such that the number of bit operations required to perform the algorithm with a k-bit input is with a big O notation k to the d. So you need a constant multiplied with this many operations to perform this algorithm. So when this is the case, it is called a polynomial time algorithm. So an exponential time algorithm can be defined as follows. It has an estimate of, again with a big O notation, e to the ck, where k is the total input length and c a constant. So as you can see, the bit length is in the exponent here. Here it is like a polynomial, so it is k to the some power, but it is an integer or some value, but not a variable. So as you can see, polynomial time algorithms would take a lot less time to perform, and exponential time algorithms will take exponential many time when the input size increases. So this is why this is one way of measuring the complexity of an algorithm. So let's see an example. Let's start with trial division. So we are trying to find the non-trivial factor of an odd integer n by trial division. This means that try all integers in the range starting from 3 to square root of n. Actually, this should be square brackets to be more mathematical, because what we will be going to do is to first check if 3 divides n. If it doesn't, then we will try 5 and so on until square root of n. We don't need to check numbers bigger than square root of n, because if we can find divisors here or none, if we find divisors here, we will divide n with that number and continue with the rest. So all of the divisors should be less than or equal to square root of n. Otherwise, n would be a prime. So we will check if any of these integers try n. So we will try one by one. So let's say that n is a k-bit integer. So log 2 to the n is k. And the number of tries we need is approximately square root of n. Actually divided by 2, but again, it is not that important because in the sake of big O notation, constants are not that important. So this is actually 2 to the k over 2. Division of a k-bit integer with a k over 2-bit integer is of O to the big O with a big O notation k to the 2. So it is k square. So we are going to perform this many divisions, and a single division requires this many bit operations. So in the notation of big O, this is the complexity of the algorithm. So as you can see, it is an exponential time algorithm. This means that if you try to find the divisors of an integer in this method, it will take exponential time. So when the size of n, the bit size of n increases, your complexity increases exponentially. So after some point on, your computational power, regardless of how many cores you have, wouldn't help you. You wouldn't be able to factorize big integers. So we are talking about this because in the RSA, we will see that security of RSA algorithm depends on the hardness of this factorization algorithm. Okay, so we talked about polynomial time algorithms, we talked about exponential time algorithms, but there are some algorithms between these two, and we define them as sub-exponential time algorithms. So let's denote them with L, but it takes two inputs. Actually, we define them with gamma and C. So a sub-exponential time algorithm has complexity, and again with the big O notation, e to the ck to the power gamma times ln k to the power 1 minus gamma. So if k is the input size of an algorithm, and if the estimate of the time cost of the algorithm is L gamma C, with gamma is between 0 and 1, the algorithm is called a sub-exponential time algorithm. So this is important because let's look at when gamma is 1. Okay, so this means that instead of gammas here, just put 1. So when you have 1 minus 1, it will be 0, k to the 0 is 1, so this cancels out. And ln1 is would be 0. Sorry, ln k will also cancel out because it is e to the power here. So we will end up with e to the ck. This part will be 1. So this means that when gamma is 1, sub-exponential time algorithm actually equals the exponential time algorithm. But if you take gamma equals to 0, this k cancels, becomes 1, so we can remove it. And this becomes ln k, but it is e to the ln k, so k comes to the beginning, so you get k to the power c. So it becomes a polynomial time algorithm. So smaller gamma means that it is closer to a polynomial time algorithm, and if it is closer to 1, it becomes closer to exponential time algorithm. So in a sub-exponential time algorithm, your aim is to have gamma as small as possible so that you have an algorithm that is faster. So we can classify algorithms in this way. This is important because in the future we will see that we won't be having a sub-exponential time algorithm to factorize, cryptanalyze elliptic curve crypto systems. For this reason, we can use shorter keys when we are using elliptic curve crypto systems. But when we will be talking about RSA, we will see that there are some sub-exponential time algorithms for factorization. For this reason, RSA keys are a lot longer. Namely, when you are using elliptic curve cryptography, using 256-bit secret key is enough. It is equivalent to the security of AES 128. But to have the same amount of security when you are using RSA, your key size should be 3092 bits, which is a lot, right, compared to the 256. So this is the reason why we use long RSA keys and short elliptic curve cryptography keys. Okay, it comes from actually this. So we will see the names of these algorithms and see a little bit detail in the following slides.